Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to revisit derived duality for finitely generated abelian groups using the most important tool in homological algebra, the long exact sequence. And we'll see that this long exact sequence will allow us to repair the main deficit with the usual duality, and that is exactness. So remember, the key obstacle is if you want to look at duality for abelian groups, that's this functor here. You look at the homomorphisms of an abelian group into Z. We'll denote that with the dual. And the point is that this is only left exact. Okay, so let's take a very, very simple example. Okay, so here we have a short exact sequence. Okay, so you have the cyclic group of order m, Z mod mz. You have a free module Z surjecting onto that in the natural way, and the kernel is mz. And so you can map onto that kernel using the multiplication by m map from Z to here. And that gives you a short exact sequence. Okay, so if this were to be an exact functor, it would mean that when you apply the duals, you'll also get a short exact sequence. What you'll find here is that the dual behaves nicely on these free modules Z and Z. They'll become Z dual and Z dual, which are just isomorphic to Z, and this is still just multiplication by m. But for this module here, we'll assume here m is some positive integer, okay? Then the dual is going to be 0. And then this sequence is no longer exact, unfortunately. Okay, the problem being that this map here is no longer surjective. Okay, so it's left exact if we didn't have the 0 here. This bit here is exact. Okay, but once we put the 0 here, for exactness here would mean that this map here is surjective, but it's not. Okay, so I want to show you how the long exact sequence can be used to repair the non-exactness that we see here. And how are we going to do that? Okay, so the first thing is I'm going to just take this blue sequence here, this short exact sequence, and I'm going to just stick it down in the bottom here. I've just rewritten it out. And the next thing that I want to do is essentially I want to look at derived functors. So I'm going to replace these essentially with some free resolution. But it turns out, remember, there's always choice in the free resolution. So we're going to do this a little bit slowly and make sure that it allows us to use the long exact sequence in homology. So we start with the Z mod mz, and we start with the free resolution of that. Well, let's just start with the beginning. We're going to take the Z which surjects onto that in the natural way. Okay, so just 1 goes to the coset of 1, so 1 plus mz if you like. And here, for this map here, just Z maps isomorphically or identically onto Z here like that. Okay. And that's fine. And we also want to have some free modules surjecting onto Z. And of course, you can pick Z here, but we want to be a little bit more careful about how we pick it. Okay, so the point is that we want something that goes in here, but it should also fill in this diagram here, okay, so that we get a short exact sequence. So the point is that if we want a short exact sequence here, I guess you have something that has a submodule Z. This will have a submodule Z and a quotient, which is this Z, such that essentially this quotient comes from modding out by the image of this Z. So it looks like we need 2 copies of Z. Okay, so we need a Z direct sum Z here. Okay, so we have a Z direct sum Z here, and we need to surject onto that. And we want to do it so that this diagram sort of commutes. Okay, so that's the other thing. So let's just see what happens here. Let's start with making sure that this diagram here commutes. Okay, so this square here commutes. So I guess what's going on here? So if you go down this way, right, you'll find that 1 here goes to 1 goes to m. So 1 goes to m here. So what's the image of this map here? This is just the first standard basis vector. Remember, this map is given by left matrix multiplication. So 1 will go to 1, 0. So 1, 0 has to go to, well, where does 1 go to here? It goes to 1, 0. So this will go to something, and that has to go to where 1 ends up here, which is m. So that means that 1, 0 has to end up to m. So if you write down what the matrix is, giving this map here, okay, the first column has to be given by m. What about the other entry over here? There's another entry. Okay, and what do you need that to be? Okay, so I guess we'll have to work that out. If you go down this way, we know what happens. Okay, so the second basis vector, that's the image of that, will end up over here. The second basis vector, okay, when you multiply it by this matrix here, okay, so that's 0, 1, okay, the column vector 0, 1, when you multiply this, you get 1, and 1 just goes to 1 here. So it seems like we want to go to 1 here, which maps to the coset 1. And now you can check that it doesn't matter whether you go around this way or you go around this way, you get the same thing. And to check that this is indeed true, you will use the fact that this m here, if you take anything in the first coordinate, it gets multiplied by m. And since it's a multiple of m here, when it goes to here, it will be 0. So essentially, you only care about what happens to the second coordinate. Okay, and we've checked that. And so here we also have a commutative square. So here, actually, what do we see here? It's quite a nice situation that we see here. What we see here is a short exact sequence here. Okay, and now we have another sequence here. This is also a short exact sequence of 3 modules. Okay, and then we have this morphism of complexes or short exact sequences, and actually you can check this map here. It is surjective. You will get 1 here. Okay, so the second basis vector maps to 1, so this is surjective, and we chose these to be surjective as well. And let's just check, I guess I forgot to mention what's happening with these maps here. Okay, so remember, to get a short exact sequence here, we decided to put the z and z together as z direct sum z. And of course, let's just check that this is indeed a short exact sequence. Okay, so if you project onto the second coordinate, that's certainly surjective. If you inject into the first coordinate, that's certainly injective. And what's the kernel of this? Okay, so I guess basically you want the second coordinate to be 0. So it's all multiples of 1, 0. So this is indeed a short exact sequence. Okay, so this is a situation that we have. And if you just look at this black bit here now, the way I'm going to analyze it is as follows. We're going to apply for the first time the long exact sequence in homology. And so remember what the long exact sequence in homology says. So basically, if we look at the homology of these, so here, yeah, you can look at this as here's a complex, and here's a complex. We go down like this. And then with these complexes, you can it's also a short exact sequence of complexes. So each of these rows is a short exact sequence, and that's why it's a short exact sequence of complexes. So that means that when you look at the homologies, so there's only going to be 2 rows of homologies, h1 on this level. So h1 of here maps to h1 of here, maps to h1 of here. And there's a connecting homomorphism to h0 of here, to h0 of here, to h0 of here. And then h minus 1, well, it's going to be zeros afterwards. So it's going to be zeros above and zeros here, rather below, and also zeros above. So let's just have a look and see what are the h1s and h0s for this black short exact sequence of complexes. Okay, so here, if you look on this 0 level, okay, it's the kernel of these maps. They all map into 0, so that's everything here, modulo the image, right? But these are all surjective maps. Remember, this is essentially the beginning of a free resolution. So you just get zeros here. Okay, so the h0s for this short exact sequence of complexes, this black short exact sequence of complexes, is just going to be 0. So all you'll have now is just what's happening with h1s. So what are the h1s? It's going to be the kernel of these maps. And the kernel will be whatever they are, modulo the image. Now the image, remember, it's just a black one, so we pad out with zeros below here and above. So the images are all zeros. So it's just a kernel. So it's just a map on all the kernels. So that means that firstly, you have a kernel functor. So this is actually something that occurs generally. The kernel is a functor. So you have a map on all the kernels of all these vertical black maps here. Okay. And in fact, that will give you a short exact sequence. Okay, so we're going to add the kernels, and I claim it's given by this blue part here. Okay, so let's just check. Here you have the identity, so the kernel is 0. Here z maps to z what mz, so the kernel is just basically mz, and we can map onto it with z multiplying by m, so that's bit there. And then what's the kernel of this bit here? I claim it's generated by 1 minus m. And one way to see that and to check is let's multiply these two matrices so that you know that the composite of these two is 0. If you multiply this m1 by this column vector 1 minus m, of course you'll get 1 times m plus minus m times 1, so that's 0. And in fact, the only solutions are just multiples of that. So certainly you'll find that the kernel of this is isomorphic to one copy of Z. That's what you expect because there's a surjective group homomorphism from two copies of Z to one copy of Z. So you expect one copy of Z here as the kernel. And it's actually given by this map here. Okay. Okay, so that's what we have. And then you'll notice that in this case here, because we're working over Z, that all of these kernels, okay, they're submodules of these free modules, so they're actually already free. And so that means that actually for each of these modules in this original short exact sequence we started with, we actually now have a free resolution if we just pad out by zeros. Okay, so we just extend by zeros here, zeros here, zeros here, and you get this free resolution. So if we look at these top two rows, I'm going to call this F double dot, okay, that's going to be a short exact sequence of free resolutions of each of these original modules that I started with, Z, Z, and Z mod MZ. Okay, so I have free resolutions of them. Okay, so that's rather nice. So we have now a short exact sequence of free resolutions. Okay, so now we're going to forget that, replace these with zeros and everything down here with zeros. And of course, there are zeros above here as well. Okay, so remember the idea of derived duality and a lot of homological algebra is you should replace a module with a free resolution. Okay, so basically we'll forget about this and we'll look at this F double dot. Okay, so let's have a look at that. And now what we want to do is we want to apply our functor, okay, our duality functor to that because the duality functor behaves nicely on free modules. Okay, so we just dualize the first two rows. Let's just see what happens. So remember the dual of Z is just naturally isomorphic to Z. Okay, so all of these Z's just become Z. So we have the same diagram here. Duality is a contravariant functor, so all the arrows go in the opposite direction. Okay, so we replace all the same modules, 0ZZ, 0ZZ, Z, two copies of Z and Z, Z, two copies of Z and Z. But now all the arrows go the other way. So this one now all goes this way. All the down arrows become up arrows, and all these right arrows in the second row go to the left as well. As for the actual morphisms here, what will happen is that all of these get transposed. Okay, so the 1 minus m becomes the row vector 1 minus m. The minus 1 is still minus 1, m is still m. Here the column 1, 0 is the row 1, 0. The row 0, 1 is the column 0, 1. And then that's what we have. Okay, so something that happens actually for free in this case is that when we take such a short exact sequence of free resolutions, if you apply an additive functor to it, you'll find that you will get a still a short exact sequence of complexes. Okay, so here's a complex that's a dual of this free resolution here. Here's a complex which is a dual. Remember, when you apply an additive functor to a complex, you get a complex. So here's a complex, here's a complex, here's a complex. They're no longer exact. Okay, even if you throw in this bit here, it's no longer exact. Okay, but you have complexes, and I'll call those complexes G prime dot, G dot, and G double prime dot. And note that you've applied a contravariant functor, so the arrows go the other way. Okay, but the most important thing is that you have a short exact sequence of complexes. And so now we can again apply the long exact sequence in homology. So let's see what that gives us. Okay, so remember this is just two rows. So this is the 0 slot. This used to be the 1 slot, but since we've applied a contravariant functor, it's now in the -1 slot. Okay, and so you don't have anything in the -2 or below slots over there, or in the 1 and higher slots over there. Okay, so that means that when you look at the long exact sequence in homology, you'll have the terms of H0 from G prime to G to G double prime, H0 from G prime to G double prime. You'll have the sequence on H1s, or H minus 1s rather, H minus 1 of G prime maps to H minus 1 of G dot maps to H minus 1 of G double prime. And then you have the connecting homomorphisms between the various homologies. Okay, so H0 G double prime will map to H minus 1 of G prime. And similarly, H minus 1 of G double prime will map to H minus 2 of G double prime, but that's going to be 0. Okay, so you've gone too far up there. So that's going to be 0. And also beforehand, you also get a 0. So there's a 0 over here. So now you have this sort of long exact sequence. So in this way, you kind of recover exactness, okay? So it's not as nice as a short exact sequence. So remember, any long exact sequence, you can think of as a whole bunch of short exact sequences. And so the information that you get from that is a little bit less elementary to work with, but still there's information that's encoded in this long exact sequence. Okay, so let's actually have a look and see what are these h0s and these h-1s. Okay, so basically what you've done is you replaced each of these modules with their free resolutions, okay, and okay, so that's what you've done here, and then you've dualized, okay, and we're looking at the homology of the dual of the free resolution. And remember, so in the h-1 slot, we just get x1 functor. So that's x1 here, the z mod mz. So for example, here you've got a free resolution of z mod mz. Okay, you dualize that, and the h-1 of that complex, okay, that dual complex is going to be x1 into z of that module, z mod mz. And similarly, we did the same thing with z here, free resolution, dual, okay, and then we take the -1 homology, that's x1 z z z, and similarly here x1 z z z. Okay, so that's what that is. And maybe we can have a look and see what that actually is. So this is the homology in this slot. So it's the kernel, which is always the whole of this, modular the image. Okay. So we've actually seen this example here. So what's the kernel here will be the whole of z modular image. That's z mod mz. So we've actually seen that before. Okay, that's what we've seen. The kernel here is z, and the image here, well, again, if you look at this, you will surject onto all of z because the first basis vector maps onto 1. So you obtain at least the subgroup generated by 1. So that's everything. So that since the image is everything, the kernel modular the image is 0. So this is 0. And so else will give 0. Although the computation works differently. It's 0 modulo the image of this, okay? So you get a 0 like that. So what about the h0? This is the thing that's rather interesting, okay? So the h0, remember, again, you'll do kernel over image. The images are all 0, so it's just the kernels of these maps. Okay, and what are all these maps, okay? So what are the kernels of these maps? So let's just take this example, okay? So here, where does this is the dual of this. So basically what you want to do is you want to take the kernel of the dual of this map. But here, remember, if you put zeros at the end here, you'll get a short exact sequence, right? That's a short exact sequence. This is a free resolution, so that you get a short exact sequence. So since you have a short exact sequence here, when you dualize this, remember, the dual is left exact. So that means that the kernel of the dual here is isomorphic to the dual of this. And the kernel of this, the dual of this map is just basically the h0 in that complex, okay? So the h0 is just going to be the dual of z mod mz. It's just the dual of z mod mz, or the homomorphisms of z mod mz into z. And similarly here, we do the same thing. Okay, so you get the dual of z, which of course is just isomorphic to z. And the same thing here, okay? This free resolution, you dual it. So the kernel of this dual map here. You can also look at it directly, compute it directly, it'll be z. Okay, and of course, what is this z mod mz dual? I guess this was, remember, the problem that we had here, and part of the reason why you don't have a nice duality theory for finitely generated abelian groups if you just use this functor is that here z mod mz goes to 0, so you've lost information. Okay, so this is a 0 here. Okay, so let's just have a look at this long sequence in homology. And really what we'll see is that, well, what's the first part here? The first part here is actually exactly what you see when you just look at these modules and you just dualize. Okay? It's all exactly the same. 0 goes to this Z mod MZ dual, which happens to be 0. Then you get this Z dual here, and then this Z dual here, right? And unfortunately, duality is only left exact, so you just have exactness up to here. And what the long exact sequence does is that, well, how does it repair the exactness of this sequence, okay? The way it repairs the exactness of this sequence is that, well, actually, we can extend this. You can't do a map to 0 here because the kernel of that is now too big. This is not surjective. You want to shrink that kernel, so you make this map over to this H minus 1, which is the Z mod MZ, okay? And this continues, so that's 0 to 0. So now when you dualize the sequence, okay, this is a 0, but you repair it by, well, you have a map from Z to Z here. That's no longer surjective, and so the bit that is missing is this quotient here, which is Z mod MZ, which comes from the x1 functor. So by throwing this x1 functor, we can restore information, okay, about this Z mod MZ, and also it fixes the exactness or the lack of exactness here, so that when you map to here, it is now exact. So this is actually looking just like the original short exact sequence, okay, but it's the dual one. Z maps to Z, okay, by multiplication by m here as well. And so the quotient of that is just Z mod MZ. But now this is realized as this extension functor, okay? So in this sense, this derived functor x1z into z restores exactness, okay? And this is just a simple example that I've given you so that you can see the elements really work in detail. But actually, it's an example of something that works quite generally. So in general, what's going to happen? Suppose you start with some short exact sequence of modules, and you want to apply some sort of functor like a hom functor or something like that, which is only left exact, okay? So the idea is, well, how can you sort of like restore, you know, exactness so that you say, well, we don't have complete information when we apply that functor, okay, but can we get some information, okay? And the point is that if you throw in some extra functors, okay, some extra what are called derived functors, okay, then you can actually give some more information about what's going on, okay? And of course, that depends on how well you can study these extra functors, okay? But the starting point is as follows. This is the general sort of setup of which this is a very simple illustrative example. It really shows you all the elements that are involved. So firstly, you start with a short exact sequence of modules like this one here. So you give this one here. And what you're going to do is you're going to build a free resolution of each of these modules. But you have to be a little bit careful. Remember how I did this. When I took a free resolution of the middle one here, I couldn't just pick Z, that's the natural one here, because if I picked a Z here, I can't get a short exact sequence with a Z here, and a Z here. Okay, there's no way you can do that. So I had to pick a Z direct sum Z. So I had to be a little bit careful. And in this case, what happens is that once I've was careful with this, I looked at the kernel of these maps and I get something free. It may be that you don't get something free, so you have to do another step and just go inductively, okay? But whatever it is, you can build a free resolution of each of the modules in your short exact sequence like this, and you're actually going to get a short exact sequence of free resolutions, okay? So next what you do is you're going to apply an additive functor to this free resolution, okay? So since you're applying an additive functor, complexes go to complexes, and since resolutions, okay, so it's not quite an exact sequence because you've dropped the original modules here, you're just looking at the free part, okay? So when you apply that, you'll only get a complex in general, okay? But what's rather nice is that actually, even though, you know, the exactness of the resolutions, okay, doesn't remain, exactness of the rows remains, and that uses the fact that we're playing around with free objects here. Okay, so I might tell you a little bit more about that in a later video. But the point is that when you apply an additive functor, like this duality functor, okay, to the short exact sequence of free resolutions, you still get a short exact sequence of complexes. And when you have a short exact sequence of complexes, the first thing you want to do is apply the long exact sequence in homology, and that will give you some nice long exact sequence, which will often restore the exactness that you get from an additive functor that otherwise might not be exact. I hope you enjoyed this adventure in pure mathematics.